Okay. What's that? So, can you see me on that little screen there?
Yeah.
Okay. So, a planetary system was discovered recently, which contains at least 7 planets similar in size to the Earth, and they're orbiting a very small star. But the planets are also at a distance from their star that would make their surface temperatures similar to the surface temperature of the Earth. So they're very interesting planets in that they're made, it's a possibility that the surfaces might be habitable. And so that's kind of the most interesting planets that people are looking for. So I'm going to talk about this planetary system. First, I want to talk about the difficulty of finding planets orbiting other stars. I'm going to set up a scale model of the solar system to illustrate the difficulty of finding exoplanets, that is, planets that don't orbit the sun, either orbiting other stars or not orbiting any stars. These little spheres are 1 millimeter in diameter. There's a penny. And that object would be the sun on that scale. So this Christmas ornament. I actually have some of these little spheres, but you can see them on here. On that scale, this would be the Earth, and that would be the sun. The sun's about 110 times bigger in diameter than the Earth is. That would be the right relative size. And on that scale, the distance between the Earth and the sun would be about 12 meters. So I'm in this classroom here. Out in the hall somewhere would be Earth. And you can see from that Earth is pretty small compared to the size of its orbit around the sun, and that the solar system is really mostly empty space. And on that scale, here we are in the E building on GPC campus, and this circle would be 10 times the size of Earth's orbit on this scale, where this is the sun and the Earth is 1 millimeter in diameter. So Saturn, which is about 10 AU from the sun, would be somewhere out on the tennis courts, and Saturn's size would be about 3/8 of an inch in diameter on that scale. And if this thing if its surface was as bright as the surface of the sun, then it would be emitting enough light to illuminate that 3/8 inch Saturn out on the tennis courts from this distance in the E building on GPC campus. And you'd be able to see that with the naked eye if there was nothing in your way and your eyes were adapted to the dark. This is 10 times the size of Earth's orbit, 20, 30, 40. Pluto is about 40 times as far from the sun, so it would be out here on Memorial Drive. Now Pluto on this scale would be only about 1/5 of a millimeter in diameter, so you wouldn't be able to see that with the naked eye. But the closer planets you can actually see with the naked eye. Now, the nearest star other than the sun on this scale would be about 2,000 miles away. So another one of these, 2,000 miles from here, and then the Earth would be one of these 1 millimeter little spheres 12 meters away from that. So if there's a planet like the Earth orbiting a star that's relatively close to us in space, that's how far away it would be, a millimeter-sized thing 12 meters from this star. And you'd be able to, the human eye would be able to see the star, if this ball were, if its surface were as bright as the surface of the sun, your eye would actually be able to see it 2,000 miles away. But what about the little bit of light from this that's reflecting off a 1 millimeter sphere 12 meters away? There's no way you could see that, right? That illustrates the difficulty of seeing exoplanets orbiting other stars, particularly when you consider that when you take an image of a star, this star is a lot brighter than, say, this star, and this pattern doesn't come from, this isn't the actual size of the star. This is an effect in a telescope called diffraction, where the light gets spread out beyond the actual position of this star. And if you want to take a picture of a planet orbiting a star, you're going to have to take a very deep image that can sense even very, very faint objects. But if you do that, then the glare of the starlight completely obliterates the image of the planet. So I'm just trying to illustrate the difficulty of seeing planets orbiting other stars. So most of the planets that have been discovered, the exoplanets, planets orbiting other stars, that have been discovered have not been directly observed because of this difficulty of seeing them. But there's a number of methods that people have used to find exoplanets. And several of them depend on the fact that when a planet orbits a star, both are really orbiting their common center of mass. So here's a planet going in a circular orbit around this star. The star is actually moving as well. A star moves in a smaller orbit. So for instance, Jupiter, its mass is about 1,000th the mass of the Sun. And so the Sun moves in a circle that's 1,000th as large as Jupiter's orbit due to the presence of Jupiter. But they do move. And if you could detect that motion in the star, you would infer the presence of the planet. And there's several ways of doing that. For one thing, say you could accurately measure the positions of many, many stars over and over. Some of them should trace out these little ovals in our sky due to the presence of a planet orbiting them. And there is a telescope that's in space doing that. It's called the Gaia telescope. It's run by the European Space Association. And one of its jobs is to very, very precisely measure the positions of billions of stars over and over and over. And it should be able to find that some of them are moving in these little ovals, indicating the fact that they're moving due to the presence of a planet. It hasn't found any so far, but the first data release was just last fall. And the people that run Gaia say that by the end of its mission, they should be able to find a few tens of thousands of planets by this method, but so far none. And I don't think any planets have been discovered using this astrometry method. But there's another way to detect the motion of the star, and that is, what I'm trying to draw here is circular orbits that are seen from an oblique angle, so that if the star is going around this way, it's coming toward the Earth and away from the Earth, toward the Earth and away from the Earth. When a light source moves toward or away from us, the motion affects the wavelength of the light. So here's a star moving toward and away and toward and away. When it's moving toward us, every successive wave of this light wave is emitted when the star is a little bit closer to us, so they kind of get bunched up, and you see a shorter wavelength, a higher frequency of light. And when it's going away, every successive wave is produced when the star is a little further away, so the wavelength gets stretched out. So and you see a lower frequency. And this is called the Doppler effect, and it occurs for any wave phenomenon. You've all experienced it with sound. Say when a propeller plane flies over your head, the sound of the plane goes like that. It drops in tone because as it's coming toward you, the frequency is higher, and as it's going away, the frequency is lower. And we perceive sound frequency as tone. So sound is a different kind of wave phenomenon from light. You know, light travels like 1,000,000 times faster, so we don't normally see the Doppler effect with light. But it's possible to use that to detect the motion of stars. This is called the radial velocity method for finding planets, because the radial velocity of an object is the velocity toward or away from us in space. And this method was the first one to be fruitful for finding planets orbiting other stars. And maybe 1,000 planets have been found using this method. There's another method that relies on the fact that, and this is the method that was used to find this planetary system, Trappist-1. It relies on the fact that there are billions of stars in the galaxy. Some of them should have their planetary orbital planes oriented such that we see them edge on from here. And that means that at some point, one or more of the planets will move in front of the star, blocking out some of the light of the star, making it appear fainter momentarily, or for a short time. And this is called the transit method for finding planets, because a planetary transit is when it appears to transit across the disk of the star, as seen from here. So this is now the most fruitful way of finding exoplanets. And here you can see a little animation of the brightness of this star going down as the planet transits across the disk of the star, as seen from Earth. And it has this very characteristic light curve shape here. It cuts it down. So, and one of the telescopes that's been used to do this is the Kepler Space Observatory. This was what it was designed to do, And I think it's probably responsible for the discovery of most of the exoplanets known so far. Here's just a graph showing the number of planets discovered as a function of year. I began teaching at this institution in '96, and there were just a handful of lectures in my astronomy class on exoplanets. But you can see that many more have been discovered now. The colors of these bars indicate the method used to discover them. So you can see most of them first were discovered using this radio velocity method, measuring the Doppler shift of the star's light. Now, the discoveries are completely dominated by the transit method. And you can see this only goes up to 2014. Graphic. But there are some other methods that I haven't talked about that people have found small numbers of planets. They're all very important methods, but I just didn't mention them because fewer planets have been found that way. Okay, so this is the way that this Trappist-1 system was found. Discovered using this telescope. Transiting planets and planetesimal small telescope south. It's operated by the University of Liège in Belgium. And the telescope itself is robotic, and it's in Chile, high in the Andes Mountains, at a very good observing site there. It's called Trappist because it's an acronym for what it is, but they also call it Trappist because Belgium is known for its Trappist ale, and this is an acknowledgement of that. So, an important planetary system named after a type of year. So this Trappist-1 system was found using this telescope. It was subsequently observed using more sensitive instruments, like the Spitzer Infrared Observatory. This is a telescope that's in space, an extremely important telescope. It's an infrared telescope, and it observed this Trappist-1 for 22 days, almost without interruption. And you can see so here's time, and these data points indicate the brightness of the star. And you can see that there are these dips, these repeated dips, many of them. Those are the transits of the various planets in this system. And these colored symbols indicate which planet is doing the transiting. So the purple symbols indicate the one that's closest to the star. And so it's happening at the highest frequency. The transits occur at the highest frequency. The red one is the next one out, and then yellow, and then this sort of brownish color, and then green, blue, and the outer one, there was only one transit in this observation, so it's this. And here are the dips in the brightness, like I showed you in that previous graphic, and there's 7 of them. Now, the interesting thing about the transit method is you can see how much of the light is blocked out, so you can infer the size of the planet compared to the size of the star, and that's how we know that these things are similar in size to the Earth. And here they are. So here's the terrestrial planets in the solar system, Mercury, Venus, Earth, Mars. And all these planets are similar in size to the Earth. And of course the appearance of them is artistic license of the painter that painted this. He's taken the liberty of putting oceans on several of them, which is probably optimistic, but we don't know. Now, what's interesting is look at the distance of the planets to the star. Earth is, by definition of this unit of distance, the AU, is 1 AU from the sun. It's about 150 million kilometers. So that unit of distance is essentially the radius of Earth's orbit. Mars is about 1.5 times further from the sun than is Earth. Venus, 0.72, Mercury, 0.39, something like that. Look at these distances, 0.011. Its distance from its star is 1.1% the size of Earth's orbit around the sun. 1.5%, 2.1. The farthest is 6% the size of Earth's orbit. Now you might say, well, they must be very hot on their surface if they're that close to their star. But they're not hot because the star is an extremely faint star. Here's the sun and the star Trappist-1. Its luminosity is this circle with a dot in it always means the sun. So L sub circle dot means the luminosity of the sun, the rate at which the sun emits light energy. So the luminosity of this object is the star is 1/1900th the luminosity of the sun. And the reason it's so faint is because it's very low in mass. Its mass is only 8.2% the mass of the sun. And that's actually about as lightweight as an object can be and still be considered a star. Astronomers have invented all these categories, mass ranges of different objects. These four categories are all called stars, and these that are lighter are substellar objects. So anything bigger than about 7.4% the mass of the sun is considered a star. And of course, stars go up to hundreds of times the mass of the sun. But now, what makes a star a star? Well, the bigger an object is, the higher its internal temperature. The mass pressing inward by gravity compresses the center and raises its temperature. If the central temperature is high enough, it causes a nuclear process called thermonuclear fusion, where protons are fused together into helium nuclei. This is the process that produces energy in the sun and most other stars. And an object has to be at least this heavy in order for that to occur. That's what distinguishes a star from a substellar object. Now, these different categories of stars have to do with differences in the behavior through their lifetimes. And, for instance, high-mass stars, their central temperatures are so high that they produce all the elements by thermonuclear fusion, then they explode and that stuff goes everywhere. And that's actually why we exist. But planets are anything smaller than about 1.2% the mass of the sun. And that's still a few thousand times the mass of the Earth. But so what we call planets are objects over a pretty wide mass range. And then there's another category between planets and stars from about 1.2% to about 7.4% the mass of the sun. And we don't call those planets, we call them brown dwarfs. The thing that distinguishes a brown dwarf from a planet is that their central temperatures are high enough to cause thermonuclear fusion of a rare isotope of hydrogen called deuterium. But it's rare, and that stuff runs out very quickly, and then the thing is just doesn't produce energy anymore. So these aren't really stars. They're not considered true stars. Red dwarfs are stars. Brown dwarfs are not stars. So these are substellar objects. These are stars. And it's pretty certain that this thing is a star. For one thing, its mass is greater than this. It's about 8.2% the mass of the sun. There's other evidence that it is a star, though, having to do with the star's spectrum. This is the spectrum of a star. I think this is the sun spectrum. The brightness as a function of the wavelength of light. The sun's light peaks at about 500 nanometers, which is what we can see. And there are these dips in the spectra of stars. Those are called spectral features. And they're due to elements in the atmospheres of the stars. And here's a section of the spectra of two different objects. So see, this line right here is a result of iron in the atmosphere. Iron. Here's a calcium feature. This one's due to lithium. Lithium is a rare light element. It's element number 3. And you see it in the spectra of brown dwarfs, but not in the spectra of red dwarfs. The reason is because if there's proton fusion occurring inside an object, it destroys lithium, and it's quickly consumed. So you don't see lithium features in the spectra of red dwarfs, but you do in the spectra of brown dwarfs. And this the spectrum of this star has been observed, and indeed it has no lithium feature. So there's pretty good confidence that it is in fact a star as opposed to a substellar object. And that, yeah, I don't know why it says, I guess that means brown dwarf, but yeah, I'm not sure why it's got that name. Maybe it was originally thought to be a brown dwarf, but now it's considered a red dwarf. Yeah, it should be RD, right? So, so now it's significant whether it's a star or a brown dwarf, or it may be significant because these are, it's a complicated graph, but these show when an object forms, whether it's a planet or a brown dwarf or a star, it comes together by gravity, and the compression causes internal heating, and that makes the the star luminous, or the object luminous. But then over time, they get fainter, and these red lines are planets. So this is a theoretical model. This one is 1,000th of a solar mass. So this would be like Jupiter. So when Jupiter formed, it was pretty luminous, and then has faded off over time. The horizontal axis is time. The green lines are brown dwarfs, and you can see they fade as well. This little kick up is due to the deuterium fusion, but then they fade out. But then stars, these are red dwarfs, they get fainter, and then they stop getting fainter because this is where proton fusion begins, and they stabilize. And these things live a really long time. Here's a calculation of lifetime as a function of mass for these objects. So the littler the star, the longer it lives. So the lightest weight red dwarf has a lifetime of something like 11 trillion years, which is nearly 1,000 times the present age of the universe. So these things have enormous lifetimes. And so this object, this Trappist-1 star, will be around for an extremely long time, which means the planetary system may be around for an extremely long time. Now, whether or not conditions will remain stable for that long, it's, we don't know. But anyway, this star will be around for a very, very, very long time, long after humans are gone. Now, one of the interesting things about this system is these planets, we don't know this yet, but these planets are probably in synchronous rotation, what's called synchronous rotation. That means that the same side always faces the star at all the time. I've tried to draw these little mountains on these planets, and the same mountains are always pointed toward the star because the same side always faces it. Synchronous rotation is common in the solar system. The moon is in synchronous rotation around the Earth, and it's caused by a gravitational interaction between an orbiting object and the orbited object if it's orbiting very close, which these are. So they're probably in synchronous rotation. So that's going to affect the conditions on the surface. Whether or not it's good for habitability or bad for habitability, nobody really knows. But they're probably in synchronous rotation. It probably is possible to find out whether or not they are eventually, but we don't yet know if they're in synchronous rotation. Now, another thing that affects whether or not these planets might be habitable has to do with the magnetic fields of the stars. There's vertical swirling of the gas inside all stars called convection. Convection occurs in the Earth's atmosphere and interior. When the sunlight heats the surface of the Earth, it heats the air, which then circulates, causing our weather. So this is convection. And in the sun, the upper layers are convective. In heavier stars, the deeper layers are convective. But in these red dwarfs, convection occurs throughout the entire interior. They call this a fully convective object. All that convection is one of the things that's responsible for generating magnetic fields. Convection inside the Earth generates Earth's magnetic field. Convection inside the sun generates the sun's magnetic field. So since these things are fully convective, they have pretty strong magnetic fields for their size. And that's significant because this is a picture of the sun in high-energy X-rays. In these high-energy photons, the surface of the sun looks very dark. That is, the part from which most of the light emits looks very dark because it isn't hot enough to emit these high-energy X-rays. But the atmosphere is, and that's caused by the magnetic field of the sun. It superheats the atmosphere, causing it to emit these very high-energy X-rays. So this is an artist's conception of what a red dwarf might look like in X-rays if you could take a picture of it close up. So it's very, very active in its atmosphere. And people have observed Trappist-1 with the XMM Newton X-ray Observatory. And indeed, it is a bright X-ray source. And it's been determined that the X-ray illuminance on these planets is many times what it is on the Earth. So now X-rays don't really bode well for habitability on the surface, partly because X-rays tend to erode atmospheres off of planets. So it may be that these planets have already had their atmospheres fully eroded away, which probably is not going to support life. Fortunately for planets orbiting these little stars, the stars start out being bright X-ray sources, then they grow fainter over time. Each one of these points represents one of these red dwarf stars, and the horizontal position is age, vertical position is X-ray luminosity. So you can see the young ones are bright and the older ones are fainter. The X-ray luminosity fades over time, and that's because the rotation slows down. Rotation is another thing that is involved in generation of magnetic fields. So they slow down in rotation. So if these planets can maintain atmospheres through the early X-ray stages of this star, then maybe later on in the history of the star, when the X-ray luminosity goes down, they can be habitable planets. Let me break away from, wait a minute, what am I doing? Break away from this, and I'm going to show you something about surface temperatures of objects. Okay, sure. Oh, yeah. Oh, thank you. There you go. Perfect. Okay, so are you ready? Okay, so what I've got here is each of these points represents one of these 7 planets orbiting the star. The horizontal axis is the distance from the star in units of the size of Earth's orbit. Vertical axis represents the surface temperature, so the closer ones are hotter. But the surface temperature depends on not only on distance from the star, but on other things, like, for example, the star's albedo, the planet's albedo, that is what fraction of the light that hits it is reflected off. And if I raise the albedo to 1 for all of these, whoa, that's not what I meant to do. If I raise the albedo to 1, the temperature drops to 0. But the lower the albedo, the smaller the fraction of light is reflected off, the warmer the planet is, because the more of that light goes into warming the surface of the planet. The Earth's albedo is about 0.35. So given that they all had Earth's albedo, this would be their approximate temperatures. And you can see that a few of them land between these 2 temperatures. These are the freezing and boiling temperatures of water. So according to this calculation, at least 2 of them would have surface temperatures in the range where water could exist on the surface. And of course, that's considered important for the existence of life because water is so essential for life. But at lower albedos, so here's a 0 albedo, and it raises all the temperatures if they're less reflective. The moon's albedo is about 0.1. Now, another thing that's important is what are the freezing and boiling points of water? That depends on the atmospheric pressure, right? Here's 1 atmosphere, and the freezing and boiling points are 32 degrees Fahrenheit and 212 Fahrenheit. But at a lower pressure, like if I go down to the atmospheric pressure of Mars, about 1/100th of an atmosphere, it's a very narrow range in which water can exist in a liquid form. So that's not as good for the existence of life. But at a higher pressure, like 100 atmospheres, this is approximately the pressure on the surface of Venus. There's a wider range in which water can exist in a liquid form. Venus, unfortunately, the temperature is above all of that. So anyway, this gives you a rough indication of what's significant for determining the surface temperature of these objects. This is a fairly crude calculation, so it doesn't tell you everything. Okay, so now, one of the interesting things about these planets discovered by the transit method is when the planet's in transit, when it's between us and the star, some of the light from the star skims through the atmosphere on its way to telescopes on Earth. And that means that the atmosphere of the planet affects the light of the star. It affects the spectrum of the star's light. And this can be used as a probe of the composition of these atmospheres of these planets. This is has already been done for a couple of these exoplanets. Here's, I don't know what planet this is, not the ones in this system, but here's wavelength, and these are measurements of the spectrum of that star's light, and these other lines are models given atmospheres of various compositions, models of what that line should look like, and that these black points roughly match an atmosphere with 100% H2O composition. So it looks like that planet has a lot of water in its atmosphere. So it's possible to do these observations to detect the composition of the planet's atmospheres. And that, of course, is significant for this, because if these planets, if we look at them for this atmosphere and they wind up having no atmospheres, that certainly doesn't bode well for life. And it's actually a pretty challenging observation to make. Here, these planets actually lend themselves quite well to this sort of study. Here's every one of these points is an exoplanet discovered by the transit method, and the height, the vertical position in here represents how easy it is to do this kind of an observation. And you can see these Trappist-1 objects are fairly high in the graph. So at least the inner three of them, the ones closest to the star, lend themselves better than most of these transit planets to study of the atmosphere. So this is surely going to be done. And one of the instruments that will make it possible is the James Webb Telescope, which is the successor to the Hubble Space Telescope. It's going to fly in space hopefully next year. And if everything works out, this should be able to study some of the most distant stars in the universe and all kinds of great stuff, including look at the spectra of this star to probe the atmospheres of its planets. And this is an estimate for the number of hours necessary of observation for these planets. The innermost planet in this system is called B, the next one is C, the next one is D, and it will take at least 70 hours of observation to detect the presence of H2O, CO2, methane, carbon monoxide, and ozone in the atmospheres of these planets. And as you can see, as the D planet will take 270 hours. Now this is hours while the planet's in transit. So it's a relatively narrow window. In other words, it'll take a long time to do these observations in order to get any reasonable answers as to the composition of these atmospheres. It's a very difficult experiment. But this should yield some information about the composition of these atmospheres if they exist. Another interesting thing about these planets has to do with the orbital periods. Here's the orbital period of the inner one. It's known quite precisely. Orbital period of the next one, next one, next. And this is the ratio of this to this. This is the ratio of this to this, the ratio of this to this, like that. Well, this ratio is close to 8 to 5, so within 0.18%. This ratio is close to 5/3, to within 0.33%. This one's close to 3/2, to within 0.4%, and 3/2, 4/3, 8/5. So what significance does this have? That means the orbital periods have simple ratios with respect to each other. This is called orbital resonance, and there's quite a few objects in the solar system that are in orbital resonance, where the period of one, like for instance, Venus orbital period is about 8/13 the orbital period of the Earth. So Earth and Venus are in orbital resonance with each other. But this is significant because it suggests that these planets form further out and have migrated their way in through gravitational interactions with other stuff in the system. If that's the case, then the planets formed in a cooler environment and so should contain volatile materials like H2O and methane and those substances that you would think would be necessary for atmospheres and living systems. So the fact that they're in orbital resonance suggests that they formed further away and then came closer to be in the warm environment that they're in. So they probably have volatiles in them. And this is roughly consistent with what we know about the densities of these planets. So here's the planets B, C, D, E, F, G. That's what they're called. And here's an estimate of the density relative to Earth. So 1 would be the same density as Earth. Now, the densities are not very well known. And this is, the uncertainty is between 0.1 and 1.6. So this one is not very well pinned down. That's because the masses are very difficult to determine. But this one's pinned down pretty well. And in fact, the density is below the density of the Earth. In other words, the density of these objects are conceivably all lower than the Earth's density. That is consistent with the notion that they contain volatile materials like these light elements that one would consider necessary for atmospheres and life. These are very poorly known densities, but they'll be better known the more this thing is observed, because they'll be able to find the masses to much greater precision. So we should know the densities of them, and it should be apparent, what kinds of substances they're made of. And that's important for considering the habitability of these planets. So this is just an artist's conception of what it might be like to be standing on the surface of one of these planets. So this is, it'll be years before we know more about this, because these observations are all very difficult. But it may turn out that the conditions on these planets are habitable. It may actually be possible to find out that there's life there, because if, for instance, they probe the atmospheres and find out there's oxygen in one or more of the atmospheres, the only reason oxygen is in the atmosphere of the Earth is because of photosynthesis. So it may actually be possible to discover life there. Another interesting thing about this, though, is these red dwarf stars, the really low-mass stars, are the most abundant stars in the galaxy. And since we've already found a very extensive planetary system orbiting one, it may be that these things are common. So there's lots of these Earth-like planets orbiting red dwarf stars. So there may be more of these things out there. So we should know, in the next 10 years is probably going to be 50,000 planets known. So, and some of them may be like this. Oh, thank you. Okay. You can ask questions because there's nobody in this room.
While they're thinking about the questions, another thought that occurred to me is time scale. You said these red dwarfs maybe.
Okay.
But the red dwarfs have, like initially when they form a large field, so there's multiple X-ray radiation, permeating the immediate vicinity, but those new planets might still be pretty far away, where they form, and then they migrate. Those are later,
right.
So that might be one reason their atmospheres and their volatile might be preserved. But also, Earth had an outgassing period that was later in its formation. So is that another reason that it may be possible for these volatile atmospheres to still be existent, even though the young star started out with a long X-ray?
Right. So if you didn't hear that question, she's asking about the X-ray luminosity of these young red dwarfs could burn off the atmospheres of planets, but if the planets started further away, they weren't so susceptible to those X-rays. And also, if they, even after the X-ray luminosity of the stars cooled down, might they still outgas? I mean, Earth is still producing gases from its interior. And the thing is, these planets have moved inward now. The star is still X-ray bright. I mean, they measured the X-ray brightness of it. So, and it's many times the luminance on the surface of the Earth due to the sun. So right now, it probably is, doesn't lend itself that well. But if these densities really are low, that means they still contain volatile substances. And so there's still more stuff to make atmosphere, right?
Yeah.
If the densities are low.
How old is the star?
They don't know how old it is. It's at least 1 billion years old, but that's all they know. It could be 10 billion, but they don't know because I can't remember. I guess it's rotation rate that's often used to calculate the age of a star. I don't think that's known yet, but yeah, but it's not very well constrained. That's another thing that'll probably be able to figure out with subsequent observations, is how old this system is. It's also, it's still X-ray bright, so it's probably not as old as some of those more faint red dwarfs.
Yeah, I could imagine that down also measure the X-ray during this regular process. It could also be a
Yeah, because there's a strong correlation between age and X-ray luminosity. Yeah, I don't know. From what I've read, they don't really feel confident about the age of this thing.